Okay, so we want to prove this PUTNAM 2002 inequality, which is basically the problem P3. And this inequality, won't be that tough to prove. We just need some Taylor series, some manipulation, and it'll be done. So the problem is for integer n greater than 1, we need to prove that 1 over 2ne is less than 1 over e minus 1 by n to the power n less than 1 by n. So yeah, to use Taylor series, so the complicated term is this one, right? So what you're gonna do is first of all separate the 1 over e, like take it to this either LHS or RHS, right? And then also multiply with -1, and then maybe take log so that n comes in front, and then take the Taylor series. So that would be our approach. So yeah, let's go ahead. So first of all, if I take 1 over e to the other sides, I get minus 1 over e plus 1 by 2 and e is less than -1 minus 1 by n to the power n is less than 1 by n e minus 1 by e. Now if I multiply by -1, I get 1 by e minus 1 by 2 n e is greater than 1 minus 1 by n to the power n is greater than 1 by e minus 1 by n e, right? Now I want to take log. Also, before taking log, we need to make sure that all the terms are positive, right? And this is in fact positive because n is positive, so 1 by 2n is going to be less than 1 by n, 1 by e, right? This is also positive term because the second one is less than first one. So yeah, since all of them are positive, so all of them are positive numbers, so we can take log. And then we also know that since log x is increasing function, the order of the inequality will remain same. It won't change because log is an increasing function. Okay, so because if it was decreasing, then this sign would have reversed. Okay, just for information. So now this becomes log of 1 by e minus 1 by 2 n e is greater than n. Log of 1 minus 1 by n is greater than log of 1 by e minus 1 by n e. Now we can make a slight manipulation over here. We can basically use the fact that we can break this as log of 1 by e plus log of 1 minus 1 by 2n, right? So yeah, if we use that, we can simply write this as -1 plus log of 1 minus 1 by 2n is greater than, this one becomes this n of log of 1 minus 1 by n, and this becomes again in the same way -1 plus log of 1 minus 1 by n. Now you can use Taylor series for log because we know that this thing 1 over n will be less than 1, cause we know that modulus of n is uh, greater than 1, right? This is less than or equals to 1 actually, because this is greater than or equals to 1, right? Sorry, this actually there's a strict inequality, yeah, because it says that it's greater than 1. So yeah, because of that we can use the Taylor series, right? Because it's less than 1. So if we use that, we get -1 plus sum from k is equals to 1 to infinity. We know that the series will be 1 by 2n to the power k by k, right? Is greater than, again, this will be sum from k equals to 1 to infinity of 1 by n to the power k divided by k is greater than -1 plus this becomes sum from k is equals to 1 to infinity of 1 by n to the power k divided by k, right? Now, I think what we're gonna do is maybe we're gonna take this n inside, right? So let's do that and see what do we get. So sum from k equals to 1 to infinity 1 by 2 to the power k n to the power k times k is greater than sum from k is equals to 1 to infinity, right? So we are just manipulating this inequality and we'll prove this at the end, right? And if we can prove its manipulation, then that's enough, yeah? 1 by n to the power k minus 1 times k is greater than -1 plus sum from k is equals to 1 to 1 to infinity. Wait, I made a slight error over here. Basically in a series of the log of 1 minus x, there's also a negative sign. I forgot that. So there's a negative sign. Yeah. Okay. I forgot that. I'm sorry for that. Also, here's negative sign. Negative sign. Okay. So yeah. So mm, okay. Now maybe we might want to make a change, right? Okay. So okay. So what we might want to do is, maybe just add one to all the sides, right? Okay. So if we just add one, okay, let's just complete this. 1 by n to the power k times k. Now if we just add 1 to all the sides, we get minus k is equals to 1 to infinity, 1 by 2 to the power k and kk. This is greater than 1 minus sum from k is equals to 1. I think there's a better way to write it. If I write from 0 to infinity, this becomes 1 by k plus 1 n to the power k is greater than a negative sum from k equals to 1 to infinity, 1 by n to the power k times k. I just rewrote the index, right? Now, the benefit of writing is like this is we can see that there's actually a cancellation over here. This is just 1 by 1 plus 1 by 1 by 1 times n to the power 1 plus 1 by 2 times n to the power 2, right? Sorry, actually there's this should be 2, this should be 3, right? Yeah. And it goes in. So the first term there's cancellation. So we see that, and that's the benefit. That gives us negative times sum from k is equals to 1 to infinity. 1 by 2 to the power k and to the power k times k is greater than this. I told you that there's this cancellation, which gives us just, okay, now this goes from 1 to infinity. I'm sorry again. 1 by k plus 1 and to the power k is greater than negative sum from k is equals to 1 to infinity, 1 by n to the power k times k. Again, let's multiply by negative 1, and that gives us sum from k is equals to 1 to infinity, 1 by 2 to the power k and to the power k times k is greater than sum from k is equals to 1 to infinity, 1 by k plus 1 and to the power k is greater than sum from k is equals to 1 to infinity, 1 by n to the power k. Now to prove this, we can actually, if we are able to prove that uh like it's actually greater even term wise, right? Each term is greater than the other, right? Then the sum of all the terms would also be bigger, right? Basically prove that the individual terms from here is bigger than that from here, then the whole sum will also be bigger than that from here, right? That's what our approach will be. And yeah, if we go with that approach, we just want to prove this one, right? To prove this, first of all, we can just cancel into the power k, right? Uh, and because we know that this is a positive number, right? And it's a positive number, and k is also a positive number. Yeah, k is basically goes from 1 to infinity. So k plus 1. Again, now to prove this, let's first reverse it. 2 to the power k times k is greater than k plus 1 is greater than k. We know that this is trivial, right? Because 1 is greater than 0, so if we add k to both sides, k plus 1 is greater than k, right? And this one is also trivial. Basically, we know that k is greater than equals to 1, right? So even for the least k, that means this becomes 2 to the power 1, which is 2, right? 2k is greater than the k plus 1. It doesn't really work for k equals to 1, but yeah, okay, what I want to see, what I want to say is over here, for k equals to 1, this is just equal, right? These are okay. It doesn't really hold for k equals to 1. These are equal, but but for all the other terms. So maybe I want to say that for 1, this is actually just equality, right? For all the other terms, for k greater than 1, this thing is bigger, right? Okay, so yeah, maybe you want to see for k equals to 2. This is just 4. Oh, it's true even for k equals to 1 actually. I'm sorry. Sorry. No, no. No, it's not. I'm sorry. I'm sorry. Okay, so for 2, this is uh, 2 to the times 2 is 4. 4k is greater than k plus 1. So, of course, this is true. You can prove this by induction, right? So, yeah, that's why this is also true. This is also true. And so that's why all the terms except for k equals to 1, but again, because we are summing it up, and while summing it off, if it's true for all the other terms, then definitely uh definitely like this one would be bigger, right? So that means but the inverse, this one would be bigger. I think I know you get the idea. Okay, so that was it. Oh, and because this is proved, that means all these are proved, and that proves our inequality. So that's how we do it. I think you get the idea, and I look forward to seeing you in the upcoming videos too. I hope you enjoyed the problem.